In the previous lecture, we discussed two control systems which are existing in a generator. One is the governing system, which ensures that the power output of a generator is controlled in and this control in fact is dependent on the frequency or the speed of the machine. The other control is the control of the excitation voltage, which typically is used to regulate the terminal voltage of the synchronous generator. Now, a synchronous generator essentially feeds a load, and the steady state behavior or the equilibrium conditions which will exist depend on the control characteristics of the generator as well as the load characteristics. So, we will just spend a little bit of time on trying to understand in a very very general way load characteristics. Now, loads come in various characteristics. For example, you got lighting loads, fans, air conditioners, industrial motors, fans, and so on. So, you will find that each of these loads have their own special characteristics. In fact, the characteristics also depend on the the volt ampere rating. For example, the small motor may have characteristics or parameters which are quite different from very large motors, right. From for example, fan motors could be of 30 or 40 watts, whereas we can have motors in industrial or power plants which are of the order of having ratings of the order of megawatts. So, there could be a large variation, and you will find that the it is difficult to characterize each and every load in the system whenever we try to do a study. The reason is that each load has different characteristics, and there are so many loads. So, each and every load to characterize may be a bit difficult, but all the same it would be nice to know what component wise how these loads behave. And when we are doing practical studies in any electrical supply system, we may actually aggregate various loads. For example, in a house we could aggregate all the lighting loads into one aggregate component, and all the fans, all the heating loads, and we could actually make several classes of loads. Okay. So, rather than represent each and every element or load element in the system, we could actually aggregate it. So, let us just have today just a quick view of what kind of characteristics we can expect out of various kinds of loads. So, if you look at the slides, you will see in fact that normally we can characterize a load by how much real and reactive power it draws. In fact, you can represent one could think of representing a load as an impedance, but not all loads are in fact what you call constant impedance type. One of the ways of representing a load is to have a simple linear dependence on the voltage and the frequency. Linear, of course, linearity will exist only if there are small changes. So, this is an approximate representation of load. So, for example, if you want to represent voltage dependence, one way of doing it is represent that load by a small correction factor, which takes into the account that the actual voltage at the bus may not be the nominal voltage, which is V naught. So, the change in power resulting due to change in voltage can be represented this is an approximate representation of a load characteristic. Similarly, reactive power also could be represented in this way. Different loads then can be simply parameterized by this KPV and KQV factors. So, this is a very approximate load representation, and since it is a kind of a linear representation, it follows that it will probably be valid only for small changes. Okay. So, not all loads will be obviously having linear variation with respect to voltage. For example, a simple heating load, the variation would be as the voltage square. Okay. So, similarly, you could also represent the variation with respect to frequency in the similar fashion. Now, why does variation with respect to frequency take place? Because you will find that many loads which include motor loads, In fact, their power which they draw from the source in fact depends on the frequency, and we will try to illustrate this using a simple example of an induction machine characteristic. Now, if you look at the typical loads which are there, for example, incandescent lights, the power factor is 1, these are typical values, and you will find that the change in power is 1.55, but this KPV factor is 1.55. It one would expect it to be exactly 2, but here you are seeing that it is not exactly 2, it is 1.55, and KQV and KPF and KQF are not dependent on so there is no dependence of reactive power on frequency, because frequency or voltage, because of course this is a real power device. So, incandescent bulb is essentially just a kind of a filament, and it does not draw any reactive power. So, you find that, and you can represent a suppose you have got a heating load. Okay, the incandescent line is not exactly a heating load, it is a lighting load, but if you have a heating load which is just a constant R, in that case your power drawn is equal to V square by R. So, this is equal to power. If there is a small change in voltage, then P will be equal to V naught plus delta V. Suppose there is a small change in voltage. So, you will have this, and this for small changes will be V naught plus 2 delta V upon R, V naught square upon 2. So, this is nothing but what you get is P is approximately equal to P naught plus 2 delta V by R, or in other words, P by P naught is equal to or maybe a better way of writing is P naught is equal to 1 plus 2 delta V upon P naught. Is there something wrong here? Yeah, it should be into V naught. So, this is into V naught by R, which is nothing but P is approximately equal to P naught. For small changes, this is delta V tends to 0. Okay. So, this is 1 plus 2 times delta V by V naught. So, this is nothing but KPV. So, we expect that a load which behaves like a constant resistance would have this kind of characteristic. Of course, if for example, this R is a function of the current, for example, you take a filament and it heats up and then its resistance changes, then of course, this KPV will come out to be different, because this R itself is going to be a function of the current. So, current is nothing but V by R again. So, you will have the characteristic here is going to be different. It is not going to be V square by a constant R, but R itself is a function of V. So, P will become a complicated function. So, this KPV will be different, but for constant R you will in fact get KPV is equal to 2. So, this is how you can in a very rough fashion get this characteristic. It is characterized very simply by this. Now, there are other kinds of loads, for example, fan motors or agricultural pumps. They are in fact not unity power factor, because they draw reactive power, and this reactive power is a function of both frequency and voltage. And similarly, in fact, even the mechanical the real power and is also a function of frequency and voltage. In fact, for agricultural pumps you will find that KPV is quite significant, and so is KPF. In fact, it is 5. That is, if the frequency falls, then the power input to the pump also reduces. So, power output of the pump also reduces. So, they will draw lesser power from the supply. So, in fact, this is one of the mechanisms other than the governors which ensures that frequency reaches equilibrium. If there is a load generation balance, then the synchronous machines tend to accelerate, but as they accelerate, there are two things which happen. One, if there is a governor, it changes the mechanical power, and if there are loads which are functions of frequency, their power also changes. So, if frequency increases, agricultural pump for example will draw more power. Okay. So, this is having a positive coefficient Kpf is useful because it kind of contributes towards coming to an equilibrium as far as frequency is concerned. If frequency increases, the power drawn also increases, okay, and that ensures that the rotating mechanical system comes to an equilibrium. So, in fact, both the governing system as well as the load frequency dependence are two factors which actually ensure that frequency reaches an equilibrium. If you have got a generator, you got a generator and which is connected to a load, and let us assume that there are no losses in transferring this power from the generator to the load, then the mechanical power is a function of frequency because of governing action, and the load also is a function of frequency. So, the solution this you can express PL to be equal to PL 0 1 plus K delta Kpf delta F by F. Let us assume that there is no voltage dependence for the time being. Suppose you have got only frequency dependence. So, this is how your load generation load dependence would be. Because of governor, you may have in steady state, this is a steady state relationship, you could have a similar relationship with Kd negative. Remember that in case frequency increases, the governor reduces the mechanical power. So, this final frequency, suppose so this the solution of this in fact will give you the final settling frequency of the system. So, you will find that when generation and load is balanced, the frequency at which that balance occurs in fact is the frequency at which the system will settle down to. Now, to understand why loads are frequency dependent, you can in fact look at the simple example of a induction machine. Remember that an induction machine is a kind of a induction motor. Let us say it is driving a fan type load. Now, a fan type load is essentially a load to the motor. So, we are talking of a motor, induction motor is connected to a fan. Now, a fan has got a certain characteristic. In fact, the load the load which comes on the motor due to driving the fan is in fact a constant into the speed of the machine square, So, in fact, so the TL is equal to omega r square divided by omega s, where omega s is they are just normalize it with the supply frequency, but essentially it is a function of the actual speed of the fan. Okay. So, omega s is the nominal speed. Okay. So, what we have here is a characteristic which is shown here, it is a quadratic characteristic, and this kind of characteristic is essentially if you have a motor which drives it. For example, if you have got a motor which has a constant torque characteristic, let us say, then wherever this two characteristics intersect, so they are not shown intersecting here, but if you have a characteristic which intersects, that is the speed at which. So, if your motor torque, the electromagnetic torque created by the motor equals to the load torque, that is the mechanical torque due to say the fan, then this is going to be the speed at which this machine will rotate at. So, this is the characteristic of fan type load. In fact, it is TL is equal to K times omega r by omega nominal, okay, rather than saying omega s, because this is a nominal frequency square, this whole thing square. So, this the speed at which the motor operates finally is dependent on these two characteristics, intersection of these two characteristics. Yeah. Now, if you look at an induction motor, you are well aware of the equivalent circuit of a induction motor, which we will not discuss here. There are many good books on how in induction motor theory. Just to you can directly work with the equivalent circuit of the motor. In fact, if you look at the equivalent circuit, it is consisting of the stator resistance, the stator leakage reactance, the magnetizing reactance, the rotor resistance referred to the stator, and the leakage of the rotor referred to the stator. And of course, this is a equivalent of what appears at the stator terminals because of the fact that the induction machine moves. So, it is like a transformer equivalent, but of course, the rotor of the machine appears to be the resistance of the machine appears to be a function of the slip. Okay. So, that is the equivalent circuit of a induction motor. The most important thing, it is like a transformer, but the rotor resistance is actually the equivalent rotor resistance which which the stator winding sees is in fact a function of the slip. So, that in fact the so called loss here is in fact it is not really a loss, not a heating loss, it is actually used to generate torque. Okay. So, this is basically the induction machine equivalent circuit, and you can in fact take an equivalent of this portion. You can in fact get a Thevenin equivalent of this, and the Thevenin equivalent voltage, open circuit voltage is VE, and RE and XE are in fact the Thevenin impedance as seen when you look into the from this point towards the left. Okay. So, this whole portion here is represented by a Thevenin equivalent. Now, once you do that, you can so the Thevenin equivalent voltage and the impedance are given by this, and the electrical torque as a result, you can show this is not proved here, but essentially the electrical torque comes out to be a function of the slip, and this omega s of course is the supply frequency, and RR is the rotor resistance. And you will find that slip is defined in this fashion: omega s minus omega r by omega s, that is slip is equal to 0 in case omega r equals to omega s. And of course, if slip is equal to 0, you will find that the torque will be in fact some some value when slip is equal to 0. Of course, it depends on how you compute this slip. You have to put limit s tending to 0. So, if you put limit s tending to 0, this will in fact come out to be 0. So, electrical torque is 0 when slip is equal to 0, and when slip is equal to 1, of course, you will get certain value. Okay. Slip is equal to 1 corresponds to 0 speed. Okay. So, slip is equal to 0 corresponds to speed being equal to omega s, and speed is equal to omega s. If you put limit s tending to 0 here, you will find that this torque also becomes equal to 0. Okay. So, this characteristic in fact looks like this. You are well aware of the induction machine characteristic. Typically, in an induction machine, we the motor operates in this region here. Okay. So, this motor operates in this region where slip is not exactly equal to 0, but slightly less than 0. So, torque is generated only if slip is slightly is not 0, but slightly more than 0. So, it cannot be exactly 0. If it is exactly 0, you have no voltage induced on the rotor, and if there is no voltage induced on the rotor, there is no current in the rotor and no torque is produced. Now, what am I getting at? Well, what is the speed at which induction machine which is connected to a fan type load rotates? You will find that it depends on the intersection of the mechanical characteristic of the fan and the electrical torque characteristic of the induction machine. So, one interesting thing is that if the frequency reduces, the intersection point changes and the electrical torque also changes. So, there is a change in power, and because there is a change in power, you will find in fact that your frequency, your power drawn by induction machine, it becomes a function of the the supply frequency. So, in fact, what we saw here, we will just go back a few slides, and what we find here is, in fact, that is what you see here. It's in fact, you can have a frequency dependence. Okay. Now, remember, of course, these values which are shown here are typical values. You will find variations in this depending on the size of the motors, and in fact, special motors may have some other characteristics. So, of course, you should not take these to be absolutely cast in stone. We have to these are only typical values. This is something we should of course remember. Now, so this is essentially what I wanted to discuss here, that your loads are in fact functions of voltage and frequency. Even reactive power and real power are functions of voltage and frequency. In discussion which we did quite some time ago, when we considered sinusoidal behavior of circuits, sinusoidal steady state behavior of circuits, we also mentioned that the total real and reactive power balance exists in a circuit. Like this total real power generated at any point, and the total rather I should say the total, there is a balance between total real power generated in the circuit and the total real power consumed in the circuit, and similarly the total reactive power generated in the circuit and the reactive power consumed in the circuit. So, eventually the system equilibrium voltage and frequency depends on this balance. So, as long as this the voltage and frequency settle down to a point where this balance is maintained. In fact, trying to find out the equilibrium voltage and frequencies and that is the steady state phasors in a circuit is often called a power flow problem. Okay. Now, many of the loads which we see here are not of constant impedance type. They are in fact they vary with respect to voltage and frequency, and therefore, we cannot often often in power systems we find that the solution of the circuit has to be the solution of a nonlinear set of equations. So, for that we require iterative methods. So, in fact, the load flow solution is an example of a system in which the network is linear, the electrical network is linear, but the loads and the generations are specified in terms of real powers, reactive powers and voltage magnitudes. In typical circuit theory problems which are done in a circuit theory course, our sources are specified as voltage sources or current sources, and we completely specify the phasors. But in a typical power flow which is done in a power system, a power flow analysis or a circuit analysis in a power system, the loads and the generations are often specified in terms of their powers. Okay. And also we often specify voltage magnitudes at various buses. This makes a lot of sense because, for example, a generator you can it naturally you can define the amount of power it generates and the voltage at its terminal, because there are two control systems which actually directly control this. So, your turbine control systems can control the amount of power output of the generator, whereas the terminal voltage is determined by the excitation system controllers, which are typically automatic voltage regulators. So, in fact, it is very natural to represent a synchronous generator as a generator whose power output and voltage is regulated. Of course, the power output can be changed in case the frequency changes. Okay. So, that is due to the governor. So, this is of course relating to the analysis of a power system. It is very important to remember of course the fact that the loads and the generators are functions of frequency and voltage, and the equilibrium is reached at the point at which all their balance exists between the voltage, the real and reactive powers in the system. Okay. Yeah. Now, we move on. While we are talking, we just mentioned about the induction motor, and this is an appropriate point to shift to another energy conversion system. We discussed about hydro and steam generators, synchronous generator basis generators, but you will find that generation of energy through wind is one of the growing sources of energy in the system. In fact, there are currently more than 440 gigawatts. This of course is slightly dated, you may have even more than this, and the power from wind is expected to worldwide is expected to exceed about 760 gigawatt by 2020, and wind turbines with individual capacities of 6 to 8 megawatt are available. So, we are talking of a single wind turbine, the ratings of up to 6 to 8 megawatt are actually available, and these wind farms may be onshore or they may be offshore, they may be located at sea, and these wind farms are a collection of several wind turbines in a certain area. These are called wind farms, and these may be hundreds of megawatts. So, this is certainly a very significant source of electrical energy. So, it is important to understand some of the characteristics of this source of energy. We did understand how, or we did a brief overview of solar power generation. Wind energy systems are of course electromechanical systems. Okay. Now, remember a few important points, that wind velocity is of course a function of height, and it varies with time. So, winds of course one can intuitively of course guess that power in the wind is of course going to be related to the wind speed, and the wind speed unfortunately cannot be predicted precisely, and but we can of course analyze it statistically. There are inherently some areas are inherently more windy than others. Okay. So, what it really means is the probability of having a higher wind speed in a certain region may be more or less than the probability of having a higher wind speed in some other region. So, actually we can characterize this kind of wind speed by a probability density function. So, probability density function effectively gives us the proportion of time spent by the wind within narrow bands of wind speed. So, you can actually tell that within in a year, for example, 5 days in a year, your wind speed was between 5 meters per second and 6 meters per second. So, this kind of characterization can be done, which will become very clear in the next slide. This is what is known as the distribution of probability density distribution. So, this of course, this distribution can be obtained only through measurements. So, we can actually take measurements over long periods of time and assume that more or less the probability can be determined by measurements taken over a long time, and mostly this kind of probability can be fit into one function. This function has been found to be reasonably give you a good fit. It has two parameters k and c, which is c is called a scale factor and k is a dimensionless shape factor. So, if I give you these two parameters and the wind speed, this probability density function usually can fit a typical, you can characterize the wind speed mostly by this is a good distribution which characterizes the speed distribution. So, for example, this is a study was carried out and you will find that different locations, this is two different locations, one in Tuticorin and one in New Kandla in India, and you will find that the mean wind speed characteristic, the probability distribution is like this. So, for example, you will find that around 2 meters per second, for a small, so if you take the area under this curve, will give you the amount of time, over a given time, how much time will the speed lie between say 2 and say 2.1. So, all you have to do is find out this area under this curve, that will give you the total probability that in a given time you will be in, your speed will be in this region. Okay. So, of course, what this when you read this, what you would say that the speed, wind speed is mostly in this lies in this region in Tuticorin, while it lies in this region in New Kandla. Okay. So, that is roughly the wind speed. Now, why is this important? That will really give you an idea what the wind speeds are, and therefore, you can design your wind turbines and also estimate how much power you can get out of these wind turbines in a given in a given time, and that is of course useful when you are planning to build a wind turbine. Yeah. Now, how do you extract power from the wind? Obviously, as I mentioned some time back, the power output of the wind will be a function of the speed of the wind itself. That is almost obvious. So, what you can think of a wind turbine as a kind of interceptor of a moving tube of wind, which is of course, if your wind turbine has got blades and it is rotating, the area which is swept by the wind turbines is called the blades of the turbine is called AW. So, if the radius of the blades is r, then AW will be pi r square. Okay. So, this is of course the cross sectional area swept by the blade. So, you are actually the wind turbine can be thought of intercepting a tube of wind which is flowing in this area AW. Of course, the mass of air flowing through this cross section in h seconds is given by AW rho into the speed of the turbine into h, where h is in second, and rho is the density of air in kilogram per meter cube, and the speed of the wind is of course Vw. Now, this amount of mass is flowing in h seconds, and therefore, the kinetic energy of this tube of wind is in fact this mass of wind in h seconds, the kinetic energy which is there in this tube is in fact half mass into speed square, and that is why we get this formula. So, in fact, the power output is when you divide it by h, you will get in fact this. Now, this is the power contained, but you can't really, this is the power. If everything was extracted out of the wind, your wind would flow past the turbine and become 0 speed after that. But of course, the blades do not completely stop the wind, it is not feasible to have such a system. So, what you actually have is only a fraction of this can be intercepted. So, the wind actually continuously flows past through the blades, and the blades are in fact moving, you are not stopping the wind by a that kind of thing, because the wind has to move past. So, you can't abruptly halt it. So, only actually a fraction of this kinetic energy can be taken out, or the power can be only a fraction of this power can be taken out, and the theoretical maximum in fact using this wind turbine blades is only 0.59. So, using a rotating blade system, you will find that you can in fact only extract 0.59 the factor 0.959 of this can be extracted from the actual available power. Okay. So, now this Cp is, as you would expect, is going to be a function of how you intercept the wind. In fact, it is a blade which is moving, and there is a tube of wind which is flowing, and there is a blade which is moving. So, it really depends on how fast this blade is moving, and it also depends on the nature of the design of the blade itself. Okay. So, in fact, Cp is dependent on the parameters of the blade and the speed at which the blades are moving. So, Cp is in fact a function of two parameters. One is called the tip speed ratio. So, in fact, just to recapitulate, you will find that in fact, the Cp factor comes in the amount of power which actually can be extracted by the wind turbine. Now, so Cp is a function of the tip speed ratio. The tip speed ratio is a function of the speed of the turbine in radian per second. So, the angular speed of the turbine is, so the Cp is a function of the angular speed of the turbine. Okay. So, so the tip speed ratio is the ratio of the tip speed, which is the angular speed into the radius, that is the speed of the tip with respect to the wind speed. Okay. So, if you have got a wind speed, and so the in fact, your Cp is dependent on the tip speed ratio. So, that the tip speed is of course dependent on the angular speed of the turbine as well as the radius of the turbine. So, these two things actually determine the tip speed ratio. So, Cp is function of this and it is also a function of the pitch angle of the blades. So, the pitch angle is in fact, if you got a blade and you turn it around, you can actually change the amount of power you can extract. So, Cp is not only a function of the speed of the tip speed in fact, but it is also dependent how you if the blade you can rotate the blade on the longitudinal axis, and the amount you rotate it in fact can change the Cp value. So, Cp value is in fact dependent on these two things, the tip speed ratio, which is in fact a function of the turbine speed and the wind speed, it is a ratio of that, and beta. Now, for any turbine you can actually fit in a curve, and this is one of the ways you can fit a curve, which is often given in the literature. The basic idea is of course that using the actual experimental data you can actually get these factors C1 to C9, and you try to fit using a numerical optimization this characteristic of the wind turbine experimentally observed to this curve. So, we have got a reference curve, and you can actually fit these by tweaking these values, you can actually get an analytical expression for this Cp as a function of lambda and beta. So, if you actually plot this for some typical values which are given in the literature, you will feel that Cp is for one particular turbine is having this characteristic. When beta is equal to 0 and I vary lambda, you will get this kind of characteristic. If I keep lambda fixed and I vary beta, you will find I will be moving along this. So, when beta is equal to 0 is let us say the point the alignment of the blade where you get the maximum power. So, if you turn around the blade, you will of course get lesser and lesser power, and of course this is the maximum value you get, this is 0.544, which is of course lower than the theoretical limit which I mentioned some time back, which is 0.59. So, for this is an example of a characteristic of a wind turbine. For various values of wind speed, you can actually calculate the mechanical power. Let us assume that beta is equal to 0, radius is 37.5, rho is equal to 1.225, and for that turbine which I showed before this, I actually plot Pm as a function of the tip speed ratio, but I do not actually take out the tip speed ratio. Remember, the tip speed ratio itself is a ratio of omega m dash r by V w. So, what we do is we actually plot Pm versus the radian speed of the turbine, and you will find that if you do this plotting, you will find that for a speed which is larger, of course, the mechanical torque, mechanical power which can be extracted increases. Now, why have I drawn this curve? Now, this is these bold lines here, these characteristics here give you the power extracted as a function of the turbine speed in radian per second. Now, since this characteristic is given to you, now what is the amount of power output you can expect out of a turbine? For example, if the wind speed is 9 meters per second, if you assume beta is equal to 0, then if my mechanical speed is 2 radian per second, the power extracted will be slightly lower than 1 here. So, just by if you know the mechanical speed, rotational speed of the turbine, then you can in fact obtain what power you are going to get out of the wind. Now, the important thing is how is the mechanical speed of the turbine, the rotational speed determined. Now, what is the turbine connected to? The turbine is connected to a generator, and the generator is connected to usually directly connected to say a grid. Let us say it is connected to a grid of 50 hertz. Now, you have got a generator which is connected to an AC grid of 50 hertz. Now, the mechanical torque speed characteristic of the generator and the turbine have to be combined in order to get the operating speed. For example, if your generator is a synchronous generator and somehow we have very gracefully somehow managed to connect it to the grid. the synchronous generator is driven by this wind turbine. Now, if your frequency of the grid is 50 hertz, then depending on the number of poles of the synchronous machine, you will be rotating at a mechanical frequency of 314 radian per second or 157 radian per second approximately. And so, if you have got a 4-pole machine, you will be rotating at 157 radian per second. Now, you also have a gear which connects the turbine, which usually rotates at a lower frequency connected to this synchronous machine. Okay. So, if the gear teeth ratio is say 75 roughly. So, you are rotating, suppose you have got a 4-pole synchronous machine connected to a 50 hertz grid, then you will have the machine running at 157 radian per second, and then you have got a teeth ratio of 75 of a gear which connects the turbine to the generator. Therefore, your speed of the turbine will be roughly 2 radian per second. Okay. So, based on that you will your intersection of 2 radian per second roughly with this will give you the operating speed, and that in fact will give you the mechanical power. Now, a synchronous machine, we know that if it is connected to a 50 hertz supply, it will also rotate at 50 hertz. Okay. So, the out terminal voltage frequency is all directly related to the rotational frequency. On the other hand, if you use some other kind of motor, say an induction motor, which is slightly different. So, for example, well, I should use the word generator, not motor here. We just in this lecture we discussed induction motor characteristic. In fact, if the speed is greater than the supply frequency, you can actually, if the mechanical speed of a motor becomes greater than the induction machine becomes greater than the supply frequency, it behaves like a generator. So, if I have got for example, a wind turbine connected to an induction machine, I will use the word machine because the machine can be operated as a motor or a generator, and this is connected to say to a 50 hertz grid. Let us say this is again a 4-pole machine, then what is the frequency of this rotation of the induction? Induction machine has got a characteristic which is given like this near the supply frequency. Okay. So, in fact, what we need to do is get this is the motor torque. Okay. So, this is the torque, electrical torque, but in the motor direction. Now, if you look at a motor, remember that in a motor the electrical torque is in this direction, the speed is in this direction, the say a fan load is in this direction. This is for a motor. For a generator, what you have is in fact, if speed is in this direction, this is the direction of the turbine torque. This is the torque of the turbine, and this is the electrical torque. Just remember that. Okay. So, what I have drawn here is a so called motor characteristic, and negative motor characteristic is in fact the generator characteristic. So, in fact, if I want to characterize the behavior of an induction generator, remember that I should reverse the torque direction. Okay. The torque direction, of course, here I have given as the motor torque is so this is for a motor. For a generator, omega greater than 0, and this will be the in fact directions of the torques. Okay. So, remember that the direction of torque is now against the direction of the speed. So, in fact, if I want to try to, so if your characteristic of the turbine is like this, this is the electrical turbine. If you connect a synchronous machine, the referred speed on one side of the gearbox and the intersection of this will actually give you the operating torque and the operating power or the power extracted from the wind and the speed. Okay. Now, in case you have got a induction machine, remember that if you have got a 50 hertz machine, the characteristic is slightly slanted. It is, remember that the electrical torque will in fact will be like this. So, you will find in fact that the characteristic will intersect this point. Remember, this characteristic is got extracted from this torque speed characteristic here, this portion. Okay. So, now you will find in fact your intersection point is slightly on this side. Okay. So, this is the referred speed, referred 50 hertz referred to the in radians per second referred to one side of the gear. Okay. Remember, of course, just to the wind turbine is usually connected through a gearbox to your generator, and this is connected to the grid. So, the grid frequency depending on the number of poles, this will be the synchronous speed of the generator will depend on the number of poles of the generator. Further, there will be again a transformation because the gear ratio. Okay. So, that in fact will this point is, so 50 hertz, this will be, if it is a 4 pole machine, 157 radian per second. If your teeth ratio is 1 upon n, in that case your referred speed will be 157 by n. Okay. So, this 157 by n will be here. Okay. Now, if it were a synchronous machine, this would be a straight line because synchronous machine is a constant speed machine, whereas for induction generator it will be having a slight slant here. Okay. So, this intersection of these two characteristics will in fact tell you at what speed you will operate and how much power you are going to get out of this machine. Now, one problem in doing this is, of course, is that suppose I have a machine which is roughly, even an induction machine is going to be roughly, with the slips are very low. So, the speed is more or less constant. So, the intersection points, for example, 7 meters per second, this would be the intersection point, very little amount of power could be extracted, very little power could be extracted here. Instead, it will be nice if you are operating at this point or at this point or at this point, right, at lower speeds, because you are at the peak. So, you are going to extract more power. But so you have to ensure that your intersection of the machine generator characteristic and the turbine characteristic occurs at this point. But of course, you can't achieve this very well with a synchronous machine, because the synchronous machine has a constant speed characteristic. Even normally an induction machine has almost constant speed characteristic, because slips operating slips are usually very small. Okay. So, you can't actually artificially ensure that you operate at this peak value and extract maximum power from the wind. So, if you want to extract maximum power from the wind, you will actually have to change the characteristic of the generator. So, that is very important. You can do that change in characteristic of a generator by changing some of the generator parameters, or use power electronics to condition the kind of voltages which are applied to the generator. Okay. So, this is the kind of thing which is done in some machines, so that you can stay on the top of this characteristic and extract maximum. Otherwise, if you do not do that, you will be simply constrained by the intersection of the generator and the turbine characteristic, and wherever it intersects is where you are going to operate. Now, typically of course, you should not exceed the nominal power of the generator, and you should also not exceed the nominal turbine speed or the generator speed. So, actually you should also, one more constraint is that you should operate in this region. Okay. So, this is one of the constraints which you also have. So, as long as you are here, there is no problem. So, you could in fact consider a synchronous machine or rather a generator which has got a characteristic such that depending on the wind speed you make it intersect at various points. Okay. So, you artificially changing the characteristic of the machine so that you can operate it. But of course, once you reach here, if you have reached the maximum speed of the turbine, then it makes sense to keep speed constant. So, if you are using a generator with some kind of control parameters, a nice idea would be to operate at low wind speeds, so that you are on the top of this characteristics. Once you hit this point, you can't increase the speed anymore further. So, you keep, because that is the rating of the machine. So, then you keep speed constant, but once you hit this, in trying to keep the speed constant, if you exceed the nominal power or the rated power of the machine, after that point you will have to spill power, you have to ensure that you do not draw. So, for example, if the wind speed becomes very high and you keep your rotation speed of the turbine and the generator turbine is kind of rotating together through the gear. So, you in fact can keep, once you exceed this rated power, you will have to, you can't in fact operate it more than the rated power. So, in such a case you will have to spill some of the power, you have to just let it go. So, you have to reduce the power output of the turbine, and that can be done by actually changing the pitch of the turbine blades. So, that is the typical control scheme which is employed for operating a wind turbine. Let me just repeat. Once you have got enough speed to generate power, if you are in the low speed region, you could in fact alter the generator characteristic, so that the intersection point between the generator characteristic and the turbine characteristic moves along this maximum power point. It is not necessary that you should be at the maximum power point. I mean, it would be desirable, because then you can extract maximum power. Okay. So, there is no compulsion of course to be on the maximum power point, but a nice strategy would be actually to stay in the maximum power point, and this is achievable only if you have got some form of control of the generator. Typical static control characteristics, that is a generator characteristics, synchronous machine or an induction machine, it is difficult to get a characteristic which will allow intersection points to move along this locus. So, you need to have some kind of control. If your speed goes beyond the rated speed, after that you need to shift over to speed regulation. So, you have to control the machine, so your speed is regulated, and in trying to maintain the speed, if the wind speed increases to a very large amount, then the power output may increase of the generator beyond its rated capacity, and if that happens, you better start reducing the power of the wind itself, and that can be done mechanically by changing the pitch angle or the rotation of the blade on the longitudinal axis. So, if you go to the next slide, we will just see some of the typical configurations which we have. In fact, one of the ways you can connect a wind turbine to the grid is directly connected to the grid using a squirrel cage induction generator, and the squirrel cage induction generator in fact is connected via gear to the turbine, and this kind of wind turbine is called type 1 turbine, and this does not in fact afford any kind of control. So, your speed is practically determined by the torque speed characteristic of the squirrel cage induction generator. As I mentioned, for large induction generators, typically the slip variation is very less, it is very small, the slip is usually small. If you go from 0 torque to rated torque of the machine, the slip variation is very small. So, for all practical purposes, the squirrel cage induction machine is almost a constant speed machine. So, in fact, your characteristic of the machine, as I mentioned, would be vertical in that characteristic which I showed some time back of the turbine. Now, this kind of scheme therefore does not allow for maximum power extraction. You have to just live with wherever the intersection points of the wind turbine characteristic and this induction generator characteristics are there. Okay. So, wherever you intersect is where you will be operating, there is no control. Okay. Of course, you need to connect the synchronous generator gracefully to the grid, and this is usually done through a soft starting arrangement. Otherwise, if you connect the generator when its speed is very much different from the grid frequency, then it will draw a large amount of current from the grid, So, that is something which is to be avoided. So, you have a soft starting arrangement. And of course, since the induction generator induction machine always draws reactive power, you need to have some kind of compensation, capacitive reactive power compensation, okay, to compensate for the reactive power drawn by this. Okay. Yeah. The other kind of generator has got a little bit of control by what we do is that this rotor winding is not a squirrel cage, it is a wound rotor induction machine. So, you actually have windings and not a squirrel cage, and that windings are in fact connected to a resistance which can be varied, that could be through power electronic means. So, you can get limited amount of changes in the the control or other characteristic of the machine by changing the resistance of the winding. So, by changing the resistance of the rotor winding, you can actually get some degree of control over the characteristic of the machine, and you can use it to slightly get better power extraction than in the first case. Okay. Now, one more important type of turbine is the type 3 and the type 4 kind of turbine. Type 3 we first consider here, where we have got a wound rotor induction generator. Of course, this line should go right down into the rotor. So, this is a minor error here. So, this actually connects to the rotor. So, what is done is the rotor windings are connected to a partial rating frequency converter. What is this converter, frequency converter? It is a back to back connected set of voltage source converters typically. So, the rotor winding is also connected to the source via a converter, voltage source converter, and you also have a crowbar circuit. Crowbar circuit is essentially a circuit which, in case there is a fault on the induction generator, near the induction generator, near the grid, in that case what we will find is that there will be large currents in the rotor windings, and this is in some ways bypassed by an arrangement called a crowbar circuit. Now, let us just look at this system here. What is this partial rating frequency converter? It is nothing but a back to back connected set of voltage source converters. So, this dabba here or this box here is in fact, this box here is nothing but this. It is a back to back connect, this and this are the voltage, so the sources on both sides. One side is the grid, for example, and the other side is the rotor windings, 3-phase rotor windings, and this frequency converter is in fact a voltage source converter, set of 2 voltage source converters acting in master slave mode. That is, this converter in fact can be controlled to extract the amount of real and reactive power you wish to, and this can be in fact pushed into this source. We actually consider this kind of combination. This is the same kind of combination you use for DC, HVDC power flow, where one of the converters pulls in power and the same thing is pushed out using the other converter. So, this converter here acts like a slave. So, whatever power it draws or supplies, either way, is actually pushed out of this, and because the if this power balance is maintained, then this capacitor voltage also, which is the DC link of the HVDC of this frequency converter, in fact is maintained. So, the frequency converter is nothing but a set of voltage source converters acting in master slave configuration. The reactive power, of course, can be controlled independently. This is something we discussed when we considered a voltage source converter in some of our previous lectures. So, both these voltage sources are in fact independently controllable. Remember, the voltage source converter, I think I forgot to show the block diagram, but that is okay. A voltage source converter is something we have discussed fairly a great amount in detail in the previous lectures. Essentially, you could have a 3-phase bridge connection of these devices, and this is in fact just a single line diagram. This is usually a 3-phase system. Okay. So, in fact, if you look at this type 3 system, what you are doing is this is actually connected to the rotor here. So, this rotor is connected to this partial frequency. So, this rotor here is called a doubly fed induction generator as opposed to a squirrel cage induction motor. So, this is in fact connected to this back to back set of master slave voltage source converter. So, it is also called a frequency converter. It is called a rotor side converter. This is the grid side converter, and you can actually control the amount of power being drawn from this rotor circuit. Now, why is this so important? The thing is that a doubly fed induction generator is exactly the kind of generator is one scheme, rather not exactly, you can have various schemes, but this is one scheme in where you can actually control the characteristic of the machine, that is the torque speed characteristic of the machine. Normally, as you know, if you take a squirrel cage induction machine, it acts like a generator in case its speed is greater than the supply frequency of the supply to which it is connected. A doubly fed induction machine, on the other hand, which is connected in this configuration, can in fact operate at speeds greater or less than the supply frequency. Okay. So, this is one interesting thing, it can still act like a generator even if the speed is less than the supply frequency. So, this how can this be achieved? If can be achieved if you understand the basics of an induction generator. Here we are using S as a slip of the machine. The slip of the machine is using generator convention, that is the slip is equal to the speed of the machine minus the supply frequency divided by the supply frequency. Okay. So, the slip is in fact we are using generator convention for slip. Slip is positive in this generator convention if the speed is greater than the synchronous speed. Now, if you have got a speed which is greater than the synchronous speed, as we know a squirrel cage induction machine would operate like a generator. Okay. Now, if you look at the power flow, let us assume that there is no frequency converter here. So, in that case you just have a let us say a squirrel cage machine. If you have got a squirrel cage machine, there is no frequency converter, and if you have got a certain mechanical power input to the generator, then Pm upon 1 plus S flows into the AC grid. So, of course, you have to subtract the stator winding loss, but Pm into S upon 1 plus S actually is available at a rotor winding, and this is in fact goes off as rotor winding loss. So, in fact, if you look at a induction generator which is a squirrel cage machine, Pm into S upon 1 plus S in fact goes off as rotor winding loss. So, and the rest in fact flows into the grid. Okay. So, depending on this, but suppose I have a frequency converter. This is in fact this what I have shown you is true of any induction generator. Okay. If you have a frequency converter, what can you do? Well, since you have got a voltage source converter here, you can adjust the output voltage of the converter and draw the power you desire, okay, provided of course it is within the rating of these converters. So, what happens is that if you draw say a certain amount of power here, let us assume that in this induction generator rotor and stator winding losses are relatively small. If you draw if you pull a certain amount of power, if you are given Pm, that would mean that the slip would be determined by how much power you draw out of this. So, in fact, you can pull a certain amount of power from this converter, in fact, can pull a certain amount of power, and therefore, it can determine the slip independently. So, that is a very important thing. If you just had a squirrel cage machine, the machine characteristic would really depend on the how much finally the rotor winding loss, stator winding, effectively on the parameters of the machine, the various parameters which are there in the machine. But now, because of the frequency controller, you can even pull a certain amount of power, and by for example, if you pull more power, your S will increase. Okay. So, you will find that your S in fact it is usually small, but you can actually increase it in case you pull more power. In fact, if you do the opposite, that is push power here, then S can become negative. So, you can in fact and S is of course we are using generator convention here. What it means is that by pushing power from this to this, you can actually make this operate at a speed which is lower than the supply frequency, and yet you can make it act like an induction generator. So, in fact, this kind of conversion system which is there in a doubly fed induction generator can help you in fact operating the machine at speeds. You can change basically the speed, torque speed or the power speed characteristic of the machine, and therefore, the intersection points with the turbine characteristic can be controlled, and especially at low wind speeds you can actually extract more power. So, this is the basic idea. So, you can actually change the characteristic of the generator. So, that is the thing you can take away from here, and once you change the power speed characteristic of a generator, you can change the intersection points with the turbine characteristic. So, the operating point may be as you would desire. So, that is the basic idea. So, these kind of controlled power extraction or scheme is possible because of the power electronic converters. Also you have got in fact other kinds of power extraction schemes where, for example, you could use a permanent magnet generator, get rid of the gear, have a high pole number machine. So, you can in fact have a full rating frequency converter which is directly connected to the stator of the machine. If this was connected to the rotor of the machine, this is connected to the stator of the machine. So, what you do is actually have a frequency converter. This, remember that the frequency here and here need not be the same. Okay. So, there is no reason why this frequency and this frequency need be the same. So, that is an important thing which you should remember. So, here if this is 50 hertz, you could have this at 10 hertz. Because you can have it at 10 hertz, you can have a machine which is rotating at a lower speed, and because it is rotating at a lower speed, you could in fact think of not having a gear and directly connecting this to the turbine. So, you could have a very low speed generator because you can now have this frequency converter connected in the path of the stator, and this of course is a completely decoupling in some sense. The frequency here and here could be different, and but however, this converter has to be the full rating because it handles the entire current which flows from the entire power which flows from here to here. In this converter system, you could actually be handling achieving control by having only partial rating. I mean, it need not be a completely fully rated. This rating of this may not be equal to the rating of the induction generator. In fact, you could tailor make this converter to have a rating so that it can achieve speed control in a certain range. Okay. So, you do not actually have to have a full rating converter. So, with this we have in this lecture understood 4 kinds of converter wind turbine generating systems. The last turbine generating system can have any kind of generator. It could be a permanent magnet synchronous machine, it could be a wound rotor synchronous machine, a typical synchronous machine, induction wound rotor induction generator or a squirrel cage induction generator, and this could be rotating. This could be a generator of a low speed design. You could possibly get possibly not have a gear, it depends on the design of course, because you can have a full rating frequency conversion which comes in the path, it just kind of separates in some ways decouples the frequency of the machine from that of the grid. Okay. The earlier type 3 turbine, you get some partial amount of control by controlling the amount of power extracted here by this voltage source converter. So, this essentially tells you how these 4 types of turbines, just this is an overview of various turbines. Remember that you could, by controlling the machine characteristics, control the power extracted from the wind, and you could preferentially try to extract maximum power from the renewable source, but it is not essential or compulsory or mandatory to do so. You could operate less or more than the maximum power, but that would actually mean that you are wasting a bit of energy. So, this kind of wind turbine, one of the things which you would have noticed is that the renewable energy systems are can be modular or come in smaller sizes, and you have got multiple units of them, and many of them in fact can be controlled by power electronic converters. They within you could in fact, because of this control, the behavior with respect to the grid actually slightly changes. A synchronous machine or an induction machine without any power electronic controller would the behavior would be determined by the mechanical and electromagnetic equations of the machine themselves. Here in addition to that, you also have the control of the power electronics, which is actually changing how the system behaves in connection with the grid. In fact, for example, in this case, if there is a grid, there is a fault in the grid, there is a short circuit, and how it affects the machine here would really depend on this control. In fact, if this control through power electronic control, voltage source converter which is here can usually control the amount of current which is going through this. So, the amount of current which is being fed into the fault can be controlled. On the other hand, if you have got a squirrel cage induction generator connected to the grid and if you have got a fault on the grid, the currents can be quite high and they are not controlled, they are simply determined by the parameters of the induction machine itself. Okay. So, actually the the power flow and its control is mediated through power electronics. Of course, in a synchronous generator there is already one power electronic element which you are aware of. The excitation system is usually also controlled using a power electronic element. So, one of the key takeaways is that with renewable energy sources like solar and wind, this power electronic interfaces are going to become more common, and that means the behavior or the dynamical characteristics is going to behave dependent on how you control these converters. Okay. So, that is the key takeaway which you should have. In the next few lectures, we will discuss the formation of a grid, and the most important thing of course, when you form a grid is the transmission lines and cables. Once we do that, we will consider generally how the grid is operated and controlled. Okay. Grid, I would say, is a collection of a large number of such generators, loads, transmission elements and so on. Okay. So far our focus in this course has been on individual elements. Even our generator, synchronous generator, we consider an individual synchronous generator. Sooner we will consider a group of such devices connected to each other, which are pooling their power, and this is essentially called a grid. So, the next lecture will be on transmission lines and cable systems, and thereafter we shall consider grid operation.